Hi everyone. So today we're going to go ahead and jump into chapter 9. So this is the dreaded unit 3 material that I've been talking about all class that is typically the most difficult for people to master. So it's really important to go through these videos and stop anytime that things are getting confusing and rewind, and also sending me any emails when things are unclear. So let me go ahead and share my screen and we will jump into the slides. Okay. So as you can see, we have lots to cover, so I'll probably break this up into 2 videos so that it's not too long. So with this chapter, we are jumping headfirst into inferential statistics. So if you remember from what we talked about in the beginning of the quarter, inferential statistics are ones that where we're taking information from a sample and making inferences about a larger population that we don't have information for. So we're going to be talking about that today. So if you remember from chapter 8 and 7, we did z-tests using sampling distributions, and this was the formula that we used. We had our sample mean, our population mean, and our standard error. So when we were running a z-test, we had all this information. We had our population mean, we had our sample mean, and we had our population standard deviation. And we use that standard deviation to derive a standard error. So that's what we were doing with the z-test. So that's what we were doing in chapter 8. However, what happens when you don't know the population standard deviation? So this happens a lot. It's very difficult to gather population data, like we've been talking about all through class. So what happens when we don't have that information? What do? Well, we estimate that standard deviation using the t-distribution. So in the past we've used the z-distribution, now we are going to be using the t-distribution. And we use this because we don't have the population standard deviation. So when you don't have your population standard deviation, you use your t-distribution instead of your z-distribution. So the t-distribution, the one that we're using in this chapter, uses sample sizes to calculate probabilities. So our n is going to be very important with this type of test. So there are different distributions for each n, or each sample size. So the biggest take-home note that I want you all to remember from here is that when we do not have population standard deviation, we use a t-test rather than a z-test. So the t-distribution is a theoretical distribution in which different curves are determined by degrees of freedom. So there's a lot happening in that definition there. First of all, we've got a theoretical distribution. And if you remember from previous chapters, we know that a theoretical distribution is one in which we use math and logic to derive probabilities. So remember that an empirical distribution, on the other hand, is the one where we have actual data. With a t-distribution, we have a theoretical distribution happening here. So we're using math and logic to determine probabilities about events. So that's what's happening with that. And we have different curves determined by degrees of freedom. So degrees of freedom is a concept in math that determines the distribution that is appropriate for the data. So basically what's happening with degrees of freedom is we are estimating the parameters that we do not know. And if you remember that from chapter 1, we talked about that a parameter is something about a population. So because we don't know a whole lot of our population data, we have to estimate it. And we do this by using degrees of freedom. So we're estimating for the different parameters that we don't know. So degrees of freedom ranges from 1 to infinity, and knowing your degrees of freedom tells you which t-distribution to use. So we have to know our n in order to calculate our degrees of freedom. So we need to know how many people we have in our sample size in order to calculate degrees of freedom, which we'll see on the next slide here. So our formula for degrees of freedom is n minus 1. So remember that n is the number of people we have in a sample minus 1. This will change up a little bit as we move through the quarter with different tests that we will be running with ANOVA and such. But for our single sample t-test, which we're doing in this chapter, our degrees of freedom formula is n minus 1. And this should be on your formula sheet, so you don't have to memorize that. So that's your formula for degrees of freedom, n minus 1. All right, so here is what your degrees of freedom looks like. If you notice here, when we have a degrees of freedom of 3, or in other words, a sample size of 4 people, we have a more fat curve. We have a wider curve happening here. However, when we double our sample size to 7, or degrees of freedom of 6, it becomes a little more normal. We see that it's becoming more of a normal curve. And when we have a degrees of freedom of infinity, it's a perfect bell curve. So we see that as we increase our sample size, we have more of a perfect bell curve. And if you remember from chapter 8, it is, I believe, there's a name for this, and it's the central limit theorem. So this is basically showing that that works for the t distribution as well here, that as we increase our sample size, our bell curve becomes more perfect and normal. So here is the t-chart that we're going to be using. So this will make more sense as we move along and talk about the different parts of a t-test, but let's call your attention to some of the features that are happening here. So we have df on the left here, so that's degrees of freedom. So in order to use this table, we have to know our degrees of freedom. So we'll need to know our n minus 1. So say we have a sample of 10 people. Our degrees of freedom would be 9. So that's how you would do that there. Some other pieces of this. We have a two-tailed test alpha level, and we have a one-tailed test alpha level. And this will make more sense as we move through the chapter, but let me draw that out so we can kind of visually see what I'm talking about here. Okay, so here's our curve. If we're wanting to do a one-tailed t-test, what that means is we are interested in one side of the curve. We're interested in, say, this part of the extreme. We could also, if we're doing a one-tailed t-test, be interested in the other side of the distribution. So these are both one-tailed examples. This is a one-tailed on the right, or a positive one-tail, and this is a one-tail on the left, or a negative one-tail. We can also do, let's see if I can do a different color. Just change this up. Okay. We can also have a two-tailed t-test, which is probably more of what we'll be doing with this chapter. And that is where we're interested in both sides of the bell curve. We're interested in the positive and the negative. So this is something that you choose. Ooh, this is not very pretty, but you get the point. So this is something that you choose before you run your t-test. You determine whether you want to do a two-tail or a one-tailed t-test. So if you're doing a one-tailed t-test, you're interested in one side of the bell curve. If you're doing a two-tailed t-test, you're interested in both sides of the bell curve. So that is the other piece here. We also have an alpha level. So that's this thing here, alpha level. And that determines how big of a colored space, a shaded space on the distribution that you want. So say you have an alpha level of 0.05, that's the most common one that we'll be using. That means that we are interested in the 5% of the distribution, that we're interested in the 5% extremes, or on the ends of the distribution. So for a one-tailed t-test with an alpha level of 0.05, what that's saying is we are interested in the either top or bottom 5% of the distribution. So that's what a one-tailed t-test with an alpha level of 0.05 is interested in. It's interested in the 5% at the top or bottom of the distribution. Say you have a two-tailed t-test with an alpha level of 0.05. We're still interested in 5% of the distribution. However, we have to cut that 5% in half on both sides. So that, if we are doing that, if we're interested in doing a two-tailed t-test with an alpha level of 0.05, what that means is that we have to break that in half so that, let me get my text out. That means that we are interested in the top 2.5% of the distribution and the bottom 2.5% of the distribution. You have to cut that 5% in half because we're interested in both the top and the bottom. So that's what that means. We can have alpha levels of different levels. We can have a 0.01, 0.001, but the most common one that we use is 0.05. So that's the two-tailed and alpha level piece of this. All these numbers here in the middle, these are our critical values. So these will come into play more when we start talking about null hypothesis significance testing. So we'll talk more about that in a minute. But these numbers in here, these are our critical values, and this is what we will need in order to determine whether our t-test is statistically significant or not. So this is basically the table that we go to in order to find out whether our data is significant. So that's what we use the t-table for. So let me clear all my drawings here. Okay. So this slide here is talking about what the rejection region, or the shaded region, the region that we're interested in, what it looks like when we have different degrees of freedom. So when we have a degrees of freedom of 2, or a sample size of 3, this is what our 5% rejection region looks like, or alpha level of 0.05 looks like. When we have a degrees of freedom of 9, this is what that alpha level of 0.05 looks like. This is what our rejection region looks like. When we have a degrees of freedom of infinity, which is impossible, but if we were to obtain that, this is what that rejection region, or alpha level of 0.05 would look like. So that's basically just showing how our normal curve becomes more normal when we increase our sample size, and how our rejection region looks when that happens. Okay, so now we're going to jump into the null hypothesis significance testing method. This method we will use throughout the rest of the quarter. The steps that we will be using, the logic and concepts that we will be talking about today, we will continue to talk about through the rest of the quarter. So it's really important that you understand this section, because we will be talking about it till kingdom come. So these are kind of the basics of the null hypothesis significance testing method. All right, so the logic of the null hypothesis significance testing method, or NHST, is that we always begin by making a claim about a parameter. And if you remember what I was talking about earlier, a parameter is some characteristic of a population. We can remember that because parameter starts with P, population also starts with P. So our population mean, the symbol is mu subscript 0. The unknown population mean, or our sample mean is another way of thinking about it, is our mu subscript 1. So we're wanting to see if these two groups are statistically significantly different or the same. That's basically our goal here. We're wanting to see if these two groups are the same or different. So we begin about making a claim about our parameter, saying that they are equal, and then we determine whether or not they are. So our NHST is a process that produces probabilities that are accurate when the null hypothesis is true. So this is really important to keep in mind. So all of the claims that we are going to be making are about the null hypothesis, and this will make more sense in a minute. But the null hypothesis argues that there is no significant difference between our two groups. So for our single sample t-test, the null hypothesis argues that there is no difference between a population and a sample. So the null hypothesis argues that there is no significant difference between a population and a sample. And we find this out by conducting our single sample t-test. We have to gather our data and conduct the test to determine whether or not our null hypothesis is true or false. This is how we do this, by using our null hypothesis significance testing method. We're making claims about whether or not the null hypothesis is true or false. So every decision that we make, every determination is about the null hypothesis, whether or not it is true or false. Okay, let me clear that. All right. So this is basically reiterating what I was saying earlier. The mu subscript 0 is talking about our population mean, and it's known. It's information that we have going in to the problem. the mu subscript 1 is an unknown population mean, and because we don't know that, we use our sample data in order to determine it. So you can also think of this as our sample mean, the data that we collect. So this is the stuff that we know, the stuff that we determine from our data that we have collected. And we compare that against our already known population mean. So this is our already known, and this is our unknown. And we want to see if these two things are comparable, if they are equal or unequal. All right. So the NHST, Null Hypothesis Significance Testing Method, is concerned with the relationship between our known and our unknown parameters, basically. So there are two possibilities. The two means can be equal, or they can be unequal or not equal. The Null Hypothesis argues that the two means are equal. So that's what this one argues. The Alternative Hypothesis, which I'll talk about on the next slide, I think, argues that the two means are not equal. So that's what's happening there. Yeah. So this is how we denote it in stats lingo. Our null hypothesis is written like this. So our mu subscript 0 is equal to mu subscript 1. So our unknown data is equal to our known, or I'm sorry, I said that backwards. Our known is equal to our unknown. The other alternative is our alternative hypothesis, so that there is a significant mean difference, so that they are unequal. So our unknown is equal to our known. So here are the actual words and symbols all put together. So the null hypothesis argues that there is no significant difference between our sample mean and our population mean. And it's written like this in our symbols. So the null hypothesis is abbreviated with an H subscript 0. And it argues that there is no significant difference between our population mean, which is this one, and our sample mean, which is this one, so that they are equal, or about equal at least. The alternative hypothesis, on the other hand, which is abbreviated H1, argues that there is a significant difference, so they are unequal from each other. So that's what the symbols look like for that one. So the alternative hypothesis argues that there is a significant difference between our two groups, between our sample mean and our population mean. It's really important that we understand this concept, again, because it will follow us till the end of the quarter. So null hypothesis argues that there is no significant difference, or that they are equal. The alternative hypothesis argues that there is a significant difference, or that they are unequal. Okay, so our book gives us an example of Doritos, of all things, and talking about whether or not a sample of Doritos that we get from a store, if the weight of those bags is significantly different from the national average of the weight of Dorito bags. So that's what this example from the book is talking about. So the average weight of Dorito bags is 269.3 grams, which is what the company claims. So that is our known, that is our population mean. That's this one here, mu subscript 0. So the null hypothesis argues that our sample mean is about equal to that. It's about equal to that average of the national average. So that's what the null hypothesis is arguing. The alternative hypothesis would be that the average weight of the chips is not equal to this 269.3 grams. So the sample that we obtain is significantly different than the national average. So that's what the alternative hypothesis would argue. So if we want to make that more clear, let's see. So this is the null. So the null is arguing that our sample and our population are about equal, and the alternative is arguing that they are unequal. There is a significant difference. So that's what's happening there. The NHST, or Null Hypothesis Significance Testing method, is a procedure that allows, if the data is good, to make strong statements of support for the hypothesis of difference. However, we always make statements about the hypothesis of equality. So this is a little confusing, but every time that we make a conclusion at the very end of our t-test problems, we're always making a conclusion about our null hypothesis. So we're saying whether or not it is true or false, whether we want to retain it or reject it. However, if our data is good, in making those claims, we can begin to make assumptions about our hypothesis of difference. So that's basically what this first bullet is saying here. The NHST cannot result in a strong support for the hypothesis of equality, regardless of how the data come out. So basically what this is saying is we can't prove whether or not the null hypothesis is necessarily true. However, we make claims about it. It's likely to be true or likely to be false. So like I said, I think in chapter 8, we don't like to use the P word. We don't like to use the word prove. So that's basically what this second bullet point is talking about here. We're never 100% certain. The logic appears roundabout, so this is a good take-home point that a lot of the claims that we make with the null hypothesis significance testing method are kind of confusing. They're kind of roundabout, so try to carry on as much as you can. It is a little confusing. However, researchers usually suspect that there is a difference between means. So we want our alternative hypothesis to be true, is basically what that's saying. We go in hoping that there will be a significant difference. To get support for this hypothesis of difference, we must rule out the hypothesis of equality. So basically what this is saying is in order to find this difference, in order to rule out all other possibilities, we've got to rule out the null hypothesis. So in order to, let's see, how should I say this? To make claims about the hypothesis of difference to gather support for it, we have to rule out the possibility that the null hypothesis is true. So basically that's what we're doing with this method. We are ruling out the possibility that the null hypothesis is true. The hypothesis is about equality produces predictions about outcomes. So this part is getting to our sampling distribution. So we use our t-test in order to determine the results about the hypothesis of equality, whether or not we should rule it out, basically. So for our book example, if the hypothesis of equality is true, that means that sample means of 269.3 grams are more likely than larger or smaller values. So basically what that's saying is if the null is true, our result should be around 269.3. So if the null hypothesis is true, our t-test result should be around this number. We should get something in this ballpark. However, if the alternative is true, we should get wildly if the alternative is true, we should get something vastly different than 269.3, something significantly different from that number. So that's how this would work in this example. If the null hypothesis is true, our data or our results are going to be around this number. If our alternative is true, or in other words, if this one is false, if our null is false, we should get something wildly different than 269.3. So that's how that works. However, some values are so far from 269.3 that they're very unlikely. And in this case, we want to reject the possibility of the null hypothesis being true. In other words, we're saying that our alternative is more likely to be true. Our alternative hypothesis is more likely to be true. So suppose the actual observations did produce a sample mean that was far from 269.3. Failure to predict the null hypothesis of equality is discredited. So basically what this is saying is that it's more likely that the alternative is true than the null. We're more likely to say that the alternative hypothesis is true rather than the null hypothesis. So in our steps with NHST, we begin by tentatively assuming that the null hypothesis is true, and then we gather data and determine whether or not it is. So we know that random samples from the population produce an array of sample means that center around that population mean of 269.3. The sampling distribution can be used to determine the probability of obtaining any particular difference. So basically what this is saying is that we use our t-table that I showed you earlier to determine the probability of obtaining certain sample means. So that's what we use that for. A large probability of a certain event can be indicative of either a null or alternative hypothesis being true. So basically what this is saying, let me draw out, okay. So say we're working with a two-tailed t-test, and we are interested in data that fall in this shaded region. This is the region in which our data start to become significant. Say we're doing a two-tailed t-test, and here is where, here's where my rejection region begins. Just because I'm anal and let's try that again. So here's my shaded region. So when my data start falling in the shaded region, we have a significant result. However, so say my sample mean falls in the blue shaded region. We reject the null hypothesis. That's what happens. So say my data fall over here. I'm going to reject the null hypothesis. It's more likely that my alternative hypothesis is true, so I'm going to reject my null hypothesis. However, let me use another color here. Say that my data falls somewhere in the middle. That's a large probability. It's in the top part of the normal curve. It's a large probability, as this is saying. When we have those instances, we can't really make claims about whether or not the null or alternative is true. Large probabilities don't permit you to adopt or accept the null hypothesis, but only retain it. So basically what this is saying is our null hypothesis is more likely to be true, but we don't know for sure. It's one of the many hypotheses that the data support. So when our data fall in the middle of the bell curve like this, we retain the null hypothesis. So let me say that again. When our data fall in the middle of the bell curve, we retain the null hypothesis. When our data fall on the extremes in the shaded region, we reject the null hypothesis. So when you get to the end of your t-test problem, you have two options. You can either retain the null hypothesis or reject the null hypothesis. When your data fall in the middle here, we retain the null hypothesis. When your data fall on the outskirts, on the edges, in the shaded regions, you reject the null hypothesis. So those are your only two options. So that's how that works. So in other words, the null hypothesis can't be proven. We just fail to reject it. So again, we don't like to use the P word, proven. So that's how that works. All right, the alternative hypothesis. So we can write the alternative hypothesis in three different ways. So remember that the alternative hypothesis is the hypothesis of difference. It's arguing that there is a significant difference between our sample and our population. So it's a hypothesis about a population parameter that is accepted if the null hypothesis is rejected. So when we reject the null hypothesis, when our data fall on the outskirts of the normal bell curve, our alternative hypothesis is more likely to be true. In other words, we reject the null hypothesis. So these are the three different ways that you write the alternative hypothesis. So this is our two-tailed alternative hypothesis. And it's going to be drawn, this is like this. This alternative hypothesis is interested in both sides of the bell curve. So that's your two-tailed null hypothesis, or I'm sorry, alternative hypothesis. This is a one-tailed. So this one is saying that our population mean is less than our sample mean. So basically, this is saying that our sample mean is bigger than our population. So it's going to be on the right side. So this is a one-tailed. So this is two-tailed. This is one-tailed. And this one is saying the opposite. It's also one-tailed. And it's saying that our population mean is going to be larger than our sample mean. So it's talking about the left side of the bell curve. Ooh. So it's talking about this one here. And this one is also one-tailed as well. This is the three different ways to do your alternative hypothesis. You can do two-tailed, and you have two different options with the one-tailed. So that's how that works. All right, if the null hypothesis is rejected, only the alternative remains. So for any NSHT problem, there are three possible alternative hypotheses. We can have our two-tailed and our two one-tailed as well. In practice, the researcher chooses one of these possible alternative hypotheses before data is collected. So in a minute, I'm going to show you all the steps that we need to do for this null hypothesis significance testing method. In one of these, before collecting data, is determining whether or not we want a one-tailed or two-tailed test. So this is something that we do before we gather data. So we determine whether or not we want to do a one-tailed or two-tailed test. And a note about that, how we determine that basically is dependent on a few things. One of them is this. So let me draw these things back up here. If we have never done research in an area and we don't really know how the data are going to fall, we're more likely to do a two-tailed t-test. Because we don't know where our data are going to fall. So if we have really no idea, it's more likely that the more prudent choice is to do your two-tailed t-test. However, if there's been some research in this area that you are delving into, you're more likely to pick the one-tailed because you kind of know where your data are going to fall. So when you don't really know, there's not a whole lot of previous research in that area, you're going to pick the two-tailed. You're going to pick this one. However, if there is some previous research in the area and you kind of know where your data might fall, you're more likely going to pick the one-tailed option. So that's that. Okay, so here is the Doritos example. Here are the three different hypotheses. Here is your one-tailed, and here is your two-tailed. So that's how that is written. The null hypothesis may be rejected or it may be retained. So like I was saying earlier, we can either retain our null hypothesis or we can reject our null hypothesis. If the null hypothesis is retained, or another way of saying that is we fail to reject the null hypothesis, there is no difference in the mean weight or grams between the sample and the population at large. So basically what that's saying is this. If we retain the null hypothesis, our rejection region is out here. Let's do this, make it a little prettier. So here's our rejection region. So if the null hypothesis is retained, there is no difference between our sample and our population. No significant difference, that is. So that means that our data are falling somewhere in this region. It's falling in that blue region. When our data fall in the blue region, we retain the null hypothesis. So retain. When it falls in the blue, we retain. When it falls in the red shaded region, we reject the null hypothesis. So, yep. So if our data fall in the red shaded region, and the rejection region is another name for it. So if it falls here on the outskirts, we reject the null hypothesis. However, if it falls in the blue shaded region here, we retain the null hypothesis. So those are our two options. Okay. So if the null hypothesis is rejected, it means that there is a mean difference in our sample and population at large in terms of our weight in chip bags. So let me draw that up here again. So if, and again here I'm doing a two-tailed example, but this could be a one-tailed, just depending on what we choose at the beginning. So say our data fall here on the edges. Our sample mean is significantly different than our population mean. In this case, we reject the null hypothesis. It's falling in the shaded regions. So that means we reject the null hypothesis. To get the probability figure for any NHST problem, you must have a sampling distribution. So for us, our sampling distribution is our T distribution. So we're going to be using our T table. For the Doritos problem, sampling distribution is the T distribution. With a sample of 8 Dorito bags, so we've got a sample of 8, our degrees of freedom is 7. We do this because we know that our degrees of freedom formula is n-1. So our sample mean was 8, so that goes here. 8 minus 1 gives us 7. So the T distribution of 7 gives you the correct probabilities. So that is our degrees of freedom. When we look at our T table, we're going to use 7 as our degrees of freedom. So let me now go to the T table really quickly. Where is it? All right. So here is our T table. This is the one that I have posted on Moodle. So in this case, remember I said we were going to do a degrees of freedom of 7. So that's what we're working with here. Say that we're doing a two-tailed t-test. So that means we're going to be working with this column here. Say that we want to do an alpha level of 0.05. That's going to be this column here. So when we look at our degrees of freedom of 7 and our two-tailed t-test, alpha level of 0.05, we see here that our critical value is 2.365. So let me draw here. So this 2.365 number is our critical value. So this is the value that starts our rejection region. In other words, for this example, let me use another. This is not very pretty, but we get the idea. Okay. 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 So at positive 2.365 and negative 2.365, that begins our rejection region. So if we get a sample mean that is bigger than 2.365 and over, we're going to reject the null hypothesis. Likewise, if we get a sample mean from our Dorito example that is to negative 2.365 or less, so over here, we're also going to reject the null hypothesis because it falls in the rejection region. However, if we get a number that is over here in the middle, we're going to retain the null hypothesis. So that's how this works. So for this example, our critical value for a two-tailed t-test, alpha level of 0.05, we have a critical value of 2.365, and because we're doing a two-tailed t-test, that is both positive and negative. So that's how that works. All right, let me go back to our slides. Okay. So if we get a sample mean that is beyond that 2.365, we're going to reject the null hypothesis, rather than conclude that we have this anomaly occurring, basically. We conclude that our null hypothesis is false. So here is basically a table that's in your book that goes through each step of the null hypothesis significance testing method with your Dorito example, and basically shows how each of those steps apply to that example. Okay, so we set our alpha level, like I was saying earlier, before we gather our data. And most of the time, the alpha level that we are working with is 0.05. However, sometimes we use other ones. But most commonly, we use an alpha level of 0.05. So we want our probability to fall within that rejection region. We want our P, which is what this stands for here, to fall within the rejection region. So say we've got a two-tailed t-test with an alpha level of 0.05. Our rejection region's over here and over here. If we've got a P level of less than 0.05, what that's saying is our data are falling out here, somewhere in here. Our data are falling there. So we have a probability of less than 0.05. So that means that our data are falling here in our rejection region. However, if we have a probability of, where's my, here we go. However, if this was reversed, greater than 0.05, in this case, that's saying that our data are falling in the middle here. In that case, we're going to retain the null hypothesis. So in this case here, we're rejecting the null hypothesis because we have a significant result. In this case, with the P greater than 0.05, we're going to retain the null hypothesis. There's no significant result. So that's how that works. All right. So significance level, we've talked about this a little bit already. We choose this before we gather our data, and it begins our rejection region. So our significance level is the point at which our rejection region starts on the normal curve. Statistically significant results are ones that fall within the rejection region. The difference between our population and our sample is so large that chance is not a plausible explanation for that difference. So we have a statistically significant result, and chance is likely not at play here. We actually have a difference happening. If we have a non-significant result happening, we're going to retain the null hypothesis. The difference is not significantly different, basically. So statistically significant in this case, here, we are going to reject the null. This case here, we're going to retain the null. So when we have a statistically significant result, we reject the null hypothesis. When we have a non-significant result, we retain the null hypothesis. In an experiment, the researcher sets an alpha level, gathers data, uses a sampling distribution to find the probability of such data. This p-value is correct only when the null hypothesis is true. So basically what this is saying is we're always making claims about the null hypothesis. And the probability of basically obtaining whatever result that we get, we're talking about when the null hypothesis is true. So if our p is less than our alpha level, we reject the null hypothesis. Basically, we are getting data that fall within the rejection region. So when p is less than a, so when our probability of obtaining this results when the null hypothesis is true, that's this, is less than our alpha level, we reject the null hypothesis. So that's saying that our data are falling in the red region here, in the red shaded region. However, if our p is greater than alpha, then that's falling here, and that means we're going to retain the null hypothesis. Thus, an alpha level of 0.05 and a p less than 0.05 or less, we're going to reject. So basically, if we have a p of 0.05 or less, that's falling here. We're going to reject the null hypothesis. However, if we have an alpha level of 0.05 and a p greater than 0.05, we retain the null hypothesis. So if we get data here, we're going to retain the null hypothesis. However, if we get data in the red shaded region here, we are going to reject the null hypothesis. It's basically how the p and alpha level thing work together. Ooh. Okay. So here is Snoop Dogg from Starsky and Hutch. He's Huggy Bear. He's saying if the p is low, the HO must go. So if p is less than 0.05, we reject the null hypothesis with just HO. Okay. When the null hypothesis is rejected, we have a statistically significant result. I already said this. When the null hypothesis is retained, we have a non-significant result. So I've already gone over this, but basically, when we reject the null hypothesis, our data are falling in our rejection region. It's statistically significant. We're good. We have differences between our two groups. When the null hypothesis is retained, our data are falling in the middle of that bell curve. We have a non-significant result, so we're going to retain the null hypothesis. Our groups are close to equal. So the rejection region, I've been throwing that word around a lot. Here's the definition for it. So it is the area of the sampling distribution that corresponds to a t-test of statistical values that lead to a rejection of the null hypothesis. So the rejection region, of course, is the point at which we begin to see significant results. So I keep drawing this lovely bell curve. And I advise you to do the same when you're working out your problem so you can visually see what's going on. So here, these two lines denote our rejection region. Ooh. Okay, I clearly don't know what I'm doing. All right, so I guess we're not using the arrows. Anyways, the lines here denote our rejection region. So that is the point at which our statistically significant area of the distribution begins. So it kind of cuts off statistically significant from non-significant. So it cuts off where we reject the null hypothesis and retain the null hypothesis. So that's what the rejection region does. Okay. Critical value. So this is the number that is associated with our rejection region for each problem. So the critical value is the number in a sampling distribution that determines whether the null hypothesis is rejected. So for our Doritos example, we found that it was the 2.365. So that was our critical value for that problem. So that is the number that separates our significant results from our non-significant results. It's called the critical value. So it's a number from a sampling distribution that determines whether the null hypothesis is rejected or not. And when we get this from the t-table, it's in your book on page 402. If the data produce t-values that are equal to or greater than the critical value and fall in the rejection region, the null hypothesis is rejected. So if our, let's draw this back up again. So we'll use the Dorito example because we already know that. So these are our critical values. For our example. So if we get a result that is in this region here, we reject the null hypothesis. So if we get a result that is -3, that falls in this region here. So we're going to reject the null hypothesis. If we get a result that is 4.2, that falls over here. We're going to reject the null hypothesis. However, if we get a result that is like 1.2, that's falling over here somewhere, we're going to retain the null hypothesis in that case. So that's how the critical value piece works. So 1.2 is less than 2.365, so we're going to retain the null hypothesis. It falls over here, so we're going to retain. Here is your T formula. Again, this will be on your formula sheet for the test. So let's talk about the different pieces here. We have T, clearly. We have our sample mean. We have our population mean. This will be given to you. And we have our standard error. So this S with the subscript X bar is our standard error. So standard error of the mean. And we find that by doing our sample standard deviation, so this S hat, over the square root of n. So you will basically have all these pieces. You will just need to put them all together to obtain your t value. So you use this formula here to get your t value. So it's very similar if you remember the z formula. It's almost identical. The only difference with that one is that we had our population standard deviation. So this was that lowercase sigma, the thing that looks like an O with a hat on it. So that's your only difference. And the reason that that's the only difference is because with the t distribution, we don't have that information. So we've got to use our sample data rather than our population data in order to find our t. So that's your difference between our t and our z, which we talked about in chapter 8. So with our Dorito example, we had our 8 bags. So say we had a mean of 270.675 grams with a standard deviation of 523 grams. Again, we're using the n-1 formula for degrees of freedom. So to test that hypothesis, we're going to use our formula here. Remember that our population mean was 269.3. So this is our sample mean. This is our population mean. This is our sample standard deviation. So we're going to take all that information and we're going to put it into the t formula. So here is our sample mean, 270.675. Here is our population mean, 269.3. Here is our sample standard deviation. And here is our n, so square root of 8. And when we do that, we get 7.44. So because we have worked ahead, because we already know that our critical value, well, actually, let me go ahead and go to the next slide before I do all that. So to interpret our t-value of 7.44 with the degrees of freedom of 7, we turn to our t-table. So we're going to find our critical value, and we're going to compare that 7.44 to determine if we have a significant result. And if you remember from when we looked at the t-table, we found that our critical value is 2.365. We found that already. But for kicks and giggles, if we want to do it again, here's our t-table. So we're doing a two-tailed t-test. So we're working with this row here. Our alpha level is 0.05, so that means that we are working with this column here. Our degrees of freedom was 7, so that means we're working with this number here, 2.365. So that's how you find that critical value. And remember that the critical value separates our significant results from our non-significant results. It is the point at which our rejection region begins. So we found that point. We found that it was 2.365. The t-test produced a larger value than 2.365. It was 7.44. And because of that, the conclusion that we need to make is to reject the null, because our 7.44 is falling in that rejection region. So let me go ahead and draw that out so that everyone can understand what I'm talking about. So we have our rejection region. And we're gonna shade that in with red. Remember that our rejection region starts at negative 2.365 and positive 2.365. So it's starting at these lines here. So that's where our rejection region starts, at the 2.365 line. Our data that we got from our t formula was 7.44. That was our t result. So 7.44 is falling way, way, way past 2.365. It's like out here somewhere. Why is it not letting me do this? Here you go. So 7.44 is like out here. It's way out there. Let me change my color. It's like over here somewhere. It's really, really far out there. So like 7.44 is really far out there. Because of that, we're going to reject the null hypothesis because our data fall in the rejection region. So we're going to reject the null hypothesis. So that is the conclusion that we come to. So this is basically showing you how to read the t-table. We've already done this. We did a two-tailed t-test. We had an alpha level of 0.05. So we go down this column here. We had a degrees of freedom of 7 because we had a sample size of 8. And our formula for degrees of freedom is n-1. So 8 minus 1 is 7. So that's this here. We go here and we find that our critical value is 2.365. So because our data are bigger than 2.365, we reject the null hypothesis. So that's all of that. So a good interpretation. So we just decided that we reject the null hypothesis. So how do we basically say that? How do we express that when we're writing up our results? Well, we want to use the terms of our experiment. We want to tell the direction of the difference between means. So you might say something like this. So when we have our project, and at the end I ask you to write a sentence, you might say something like this: the null hypothesis was rejected. At the national average, I guess. Okay. So we could say something like a sample Okay, so the null hypothesis was rejected. Cool, we know that. So we're suggesting that there is a significant difference between the sample mean weight of Dorito bags when compared to the national average weight of Dorito bags. So I'm saying that there is a significant difference between our sample and our population, and I'm using the terms of the experiment. I'm saying that we're talking about the weight of the Dorito bags. So that's using the terms of the experiment. Number two, we want to talk about the direction of the difference between the means. So that's the second sentence I wrote here. The sample was significantly heavier than the population. So the sample bags were significantly heavier than the population average bags were. So this is how you would write up your results for a t-test. You want to talk about the terms of the experiment, so what variables are being used, and you want to talk about the direction of your results. So I said that our sample was significantly heavier, and I know that because our sample mean was 7.44, and our critical value was much less than that, the 2.365. So we have a greater difference there. Okay, so this is a little note of more about kind of research in general. So in order to generalize our results to the population at large, to make statements about the population, to make inferences, we want to generalize our results. Of course, we want to make those inferences about the population. But in order to do that, we need to do random assignment. And I believe I've talked about this in the past. So random assignment is where everybody in the, so random, I'm sorry, subjects, participants, study are randomly assigned to the experimental groups. So when we use random assignment, we can be more certain. Ooh, what did I just do? Go away. Okay, so when we use random assignment, when we randomly assign our participants to groups, we can be more certain about our results. We can be more sure when we are generalizing because we have used that randomization. Another good thing that another good technique to keep in mind, in addition to random assignment, is random sampling, which I talked about, I believe, in chapter 8. So this is where everyone in a population has an equal chance of being selected for a study. So when we use random sampling on top of random assignment, you're pretty good. You're in a good spot to make generalizations about the population at large because you have randomized your sampling methods and your assignment into experimental groups. So when we use these two things, we can be pretty confident in our generalizability to that population at large. We can make conclusions about the actual population. So when we use random sampling and random assignment, we're in a good spot. Okay, I'm gonna go ahead and pause there and start our next video with type 1 and type 2 error. Stop sharing.